So, continuing on with our lecture of chapter 4, in this next section, we're going to be discussing mass to atom conversions. So, using the molar mass or atomic mass and Avogadro's number, we can calculate the atoms of an element and a sample of that element. Now, your molar mass can be in AMU or gram per mole. So, just to fill in our problem-solving scheme once again, to go from atoms and molecules to moles, what we have to do is we have to divide by Avogadro's number, which is 6.02 times 10 to the 23rd. If we want to go from moles to molecules or atoms, we multiply by Avogadro's number. Now, how do we get to moles from mass? Well, to go from moles to mass, we have to go from moles to mass, we would multiply by the molar mass or molecular weight. If we want to go from mass to moles, we divide by the molar mass or molecular weight. Now, let's show an example of this. We're asked how many atoms of iron are in 33 grams of iron. So we're going from grams of iron to some units to atoms of iron. And in this case, our intermediate stepping stone unit is moles of iron. Okay, we can go from mass to moles, and I like to fill in this kind of scheme with the conversion factors. To go from mass to moles, I'm going to divide by my molar mass. To go from moles to atoms, I'm going to multiply by Avogadro's number. We can see that if we perform unit analysis the traditional way. I just like to make the problem-solving process as clear as possible, so that way I don't make any errors. So I have 33 grams of iron. Since we're going to moles, moles are on top, so we have 1 mole of iron. And would someone like to tell me what is the atomic mass of iron? What is the atomic mass of iron? Don't be shy to break out your periodic table. Yeah, about 55.7. Yep, perfect. And then we know that there are 6.02 times 10 to the 23rd atoms of iron in 1 mole of iron. Grams cancel, moles cancel, and we're left with atoms of iron. Let's now punch this into our calculator. And let's see what we get. One moment, just punching this into So we're going to take 33.0 divided by 55.7 times 6.02 times 10 to the 23rd. And that in turn gives us 3.57 times 10 to the 23rd iron atoms. And always make sure you label your units. Any questions on this example? Let's do another example. So we're asked to figure out the mass in grams of 1.51 times 10 to the 22nd molecules of calcium hydroxide. So let's do a sidebar calculation. The molar mass of calcium hydroxide is equal to the mass of calcium, which is about 40 grams per mole, plus the mass of oxygen, which is about 16 grams per mole, times the number of oxygen atoms. Since we have 2 oxygen atoms, we multiply it by 2, plus the molar mass of hydrogen times the number of hydrogen atoms. And that gives us the molar mass of calcium hydroxide is equal to 74 gram per mole of calcium hydroxide. I always like to put my unit labels as they save me a lot of grief when I'm going through and I'm checking to see that the units cancel. Okay, continuing on with this, we're asked to go from molecules of calcium hydroxide to some unit to grams of calcium hydroxide. For our intermediate unit, we're going to go through moles. Okay. So again, just to fill out our problem solving scheme, to go from molecules to moles, we're going to divide by Avogadro's number. And to go from moles to grams, we're going to multiply by the molar mass. So now that we have this problem solving scheme filled in, we know that we have 1.51 times 10 to the 22nd molecules. And we know that in 1 mole of calcium hydroxide, there are 6.02 times 10 to the 23rd molecules of calcium hydroxide. Then, if we want to go from moles to mass, we know that we have 74 grams per every 1 mole of calcium hydroxide. And that in turn, once we punch this into our calculator, so we have 1.51 divided by 6.02 times 74. And that in turn gives us 1.86 grams of calcium hydroxide. So let me make that a little bit neater. Any questions on these examples? Any questions on these examples? If not, let's now attempt in a problem-solving session the following 2 conversions. So I'd like you to tell me the mass in grams for a known number of atoms of sodium, and I'd like you to tell me the molecules of mercury oxide in 200 grams of mercury oxide. And you're more than welcome to enter your responses in the chat or through Canvas, as this is found in Canvas Quiz 4.3.3. So let's spend about 4 to 5 minutes working through these 2 problems, and then we'll come together as a group to discuss. And I'll be checking to see how everyone's doing on these questions and if there are any common errors I can address. And if there are any questions, don't be shy to submit them in the chat. So I'm seeing reasonable responses so far. Let's try to get a few more student responses, both via Canvas or in the chat, and then we'll discuss this problem momentarily. Let's try to get a few more responses in Canvas in the chat. If you have any questions, don't be shy to ask them in the chat or unmute and ask your questions verbally. And we'll spend about another 3 to 4 minutes on this problem. And thank you for providing your responses via Canvas and in the chat. And we'll discuss this example momentarily. Let's try to get a majority of the class responding, just so that way when we go through the solution, you can compare the logic you use to generate your solution to the logic that I'm using when I'm solving these problems. And if there are any questions, don't be shy to ask them in the chat. And we'll discuss in a few minutes, in about 2 minutes. Let's try to get a few more responses, and then we'll discuss in about 1 minute. Okay, so let's discuss these examples now. So we're asked to figure out the mass in grams of 8.6 times 10 to the 22nd atoms of sodium. So we're going from atoms of sodium to some unit to grams of sodium. Our intermediate stepping stone will be moles of sodium. So just to fill in the blanks here a little bit, to go from atoms of sodium to moles of sodium, we're going to divide by Avogadro's number, and to go from moles to grams, we're going to multiply by the molar mass. So now that we have everything laid out for us, let's just plug in our numbers. We have 8.66 times 10 to the 22nd grams of sodium. And we know that in 1 mole of sodium, we have approximately 23 grams of sodium. Now, if we're going from, whoops, sorry, this isn't grams. We're starting from atoms. Let me correct that. Got a little bit ahead of myself there. So starting from atoms of sodium, we know that in 1 mole of sodium, we have 6.02 times 10 to the 23rd atoms of sodium. So our atoms cancel, we're left with moles. Now to go from moles to grams, grams go on top, and we have 23 grams of sodium in 1 mole of sodium. Moles cancel, we're left with grams, and now all we have to do is punch this into our calculator. So let's do just that. So we have 8.66 times 10 to the 22nd divided by 6.02 times 10 to the 23rd times 23. And when we punch this into our calculator, just double checking I entered everything correctly, we would get 3.31 grams, roughly. If you use a slightly more precise atomic mass, your number will be a little bit different. So this 23 is our atomic mass. And as we discussed last session, if you look in the periodic table, under your element symbol, you'll see a number of about 22.98. And this is our atomic mass for that element. So we can calculate the atomic mass and molar mass by looking at the periodic table. And if we have a molecule, we can calculate the molecular weight by adding up our atomic masses. Let me take a look. I can certainly check that. Let's see what the response was provided. Yeah, let me just correct that really quickly. Okay, so let's now look at the, yeah, sorry about that. There was an error when I was transferring the question over in Canvas. 3.31, as we found working through this problem, is the correct mass of sodium for this number of atoms of sodium. Let's now look at another example. How many molecules of mercury oxide are in 200 grams of mercury oxide? In this case, we're going from grams of mercury oxide to some unit to molecules of mercury oxide. Our stepping stone, again, we're going through moles of mercury oxide. And following our problem-solving scheme, to go from grams to moles, we're going to divide by the molar mass. To go from moles to molecules, we're going to multiply by Avogadro's number. Remember, anytime you're talking about particles, be them atoms or molecules, you are likely going to have to use Avogadro's number in some form. So now that we have everything laid out for us, let's now execute on this scheme. So we have 200 grams of mercury oxide. We're going to need to do a sidebar calculation. So the molar mass of mercury oxide. So first and foremost, we need to find the molar mass of mercury. We need to find the molar mass of mercury. So let's pull out our periodic table. And would someone like to volunteer and tell me the molar mass of mercury, which has the symbol Hg? What is the molar mass of mercury? If you're reading through your periodic table, I just want people to be comfortable accessing this critical information from the periodic table. The molar mass of mercury is 200.6. Okay, plus the mass of oxygen, which is 16.0, and that gives us 216.6 gram per mole. Perfect. Now that we have our molar mass, we know that in 1 mole of mercury oxide, we have 216.6 grams. Grams cancel. And now to go from moles to molecules, we know that there are 6.02 times 10 to the 23rd molecules in 1 mole of mercury oxide. Moles cancel. We're left with molecules. And now all we have to do is punch this into our calculator. So we have 200 over 216.6 times 6.02 times 10 to the 23rd. Checking I entered everything correctly. We should end up getting, in the end, 5.55 times 10 to the 23rd, which we in turn round, since we only have one sig fig, to 6 times 10 to the 23rd. Any questions on these examples? If not, let's try a few more examples. This time, we're going to deal with mass to mole and atom to mole conversions, this time if we're given the formula as a name. So it's asking how many formula units of potassium sulfite are present in 20.3 grams of potassium sulfite. So first things first, we need to figure out the formula of potassium sulfite. Would someone like to volunteer in the chat or verbally? Would someone like to volunteer the formula of potassium sulfite? Would someone like to volunteer the formula of potassium sulfite?
K2SO3.
Yep, exactly right. So potassium is K plus, sulfite is SO3 2 minus. We cross our charges and we get K2SO3. So this is potassium sulfite. Okay. Now in our scheme, we're going from grams of potassium sulfite. And our end goal is formula units of potassium sulfite, which you can think very similarly to molecules of potassium sulfite. So we want formula units of potassium sulfite. And just like any typical mass to particle conversion, we're going to go through the moles of potassium sulfite. Now, in terms of what we need to actually solve this problem, to go from grams to moles, we're going to divide by the molar mass. To go from moles to formula units, we're going to multiply by Avogadro's number. Now that we have our scheme in place, we can execute. Now, since we need the molar mass, let's just quickly figure out the molar mass of potassium sulfite. So potassium has a molar mass of 39 gram per mole. We have 2 potassium atoms. Sulfur has a molar mass of 32 gram per mole. We have 1 sulfur atom. And oxygen has 16 grams per mole as its molar mass, and we have 3 oxygen atoms. So for our molar mass of potassium sulfite, let's just punch that into our calculator really quickly. We get a molar mass of 158 gram per mole. Wonderful. Now that we have all this preliminary information laid out, let's execute on our unit conversion. So we start with 20.3 grams. We know that in 1 mole of potassium sulfite, we have 158 grams. Grams cancel. Now to go from moles to formula units, we know we have 6.02 times 10 to the 23rd formula units per 1 mole of potassium sulfite. Moles cancel. And now all we have to do is punch this into our calculator. And that in turn gives us 7.73 times 10 to the 23rd formula units. So the only thing that's new is now you have to get the formula from the name. So it tests your knowledge of chapter 3 and your knowledge of nomenclature. Do these examples make sense so far? Any questions so far on these examples? Whoops, yes, this should be 10 to the 22nd. Yep, perfect. Any other questions on these examples? If not, what I now like us to do is to take about 3 minutes and work on the following example. I'd like you to tell me the mass in grams of 4.63 times 10 to the 22nd molecules of phosphorus pentachloride. So again, you're doing a molecule to mass conversion this time. This can be, you can submit your responses in the chat or in Canvas quiz 4.3.4. And we'll discuss in about 3 minutes. And if there are any questions, don't be shy to unmute and ask your question verbally or to ask your question in the chat. So let's try to get a few more responses in the chat or via Canvas, and then we'll discuss in about 2 minutes. And if there are any questions, don't be shy to ask them. Let's try to get a few more responses. We have a lot of reasonable responses so far via Canvas. And if you want me to check your response, don't be shy to message me with a private message via Zoom, and I can certainly provide feedback on this problem. If not, we'll discuss in about another minute. Okay, so let's now discuss this next example. Okay, phosphorus pentachloride. It's a covalent compound. I'm gonna need your help here. What is the formula of phosphorus pentachloride? What is the formula of phosphorus pentachloride? PCl5, exactly. Phosphorus, so we only have one phosphorus atom. Penta is 5, so PCl5. Let's calculate the molar mass. So phosphorus is 30.9 gram per mole times one phosphorus atom. Chlorine is 35.5 gram per mole. And we have 5 phosphorus atoms. So let's, we have 5 chlorine atoms. So let's now punch this into our calculator. That in turn gives us 208.4 grams per mole of phosphorus pentachloride. Okay, so now we're going from molecules of phosphorus pentachloride, and we're trying to calculate the grams of phosphorus pentachloride. We're going to go through moles of phosphorus pentachloride. So in order to execute on this conversion, to go from molecules to moles, we're going to divide by Avogadro's number, and to go from moles to grams, we're going to multiply by the molar mass. So then, starting with 4.63 times 10 to the 22nd molecules of phosphorus pentachloride, we know that in 1 mole of phosphorus pentachloride, we have 6.02 times 10 to the 23rd grams. Now, 10 to the 23rd molecules. Now to go from moles to grams, grams are on top, and we know that we have 208.4 grams per 1 mole of phosphorus pentachloride. Molecules cancel, moles cancel, and let's punch this into our calculator. We have 4.63 times 10 to the 22nd over 6.02 times 10 to the 23rd. Remember to enter the number and the power of 10 together in parentheses to avoid calculator errors, times 208.4. And that in turn gives us 16.0 grams of phosphorus pentachloride. Does this example make sense to everyone? Is everyone getting the hang of these mass to mole to atom conversions? It's exactly identical to the logic we used when we did mass to particle conversions using AMU. Any questions on these examples? If not, let's keep going with a few more ideas. So the next major idea that we're going to introduce is this idea of the chemical formula. So the chemical formula provides us a pretty interesting relationship between the moles of molecules and the moles of atoms of an element in that molecule. So the chemical formula provides us a way to go from molecules to atoms. And that's not all. The chemical formula also gives us a relationship between the moles of atoms of an element, so atoms 1, and the moles of atoms of another element in that molecule. So we can go from moles of molecules to moles of atoms, and we can also go from moles of atoms 1 to the moles of atoms in another element that we'll call moles of atoms 2. Now, the formula ratio there are two main definitions for the formula ratio. It's the ratio of the moles of an element to the moles of a compound, or it can be thought of as the ratio of the moles of one element in a compound to the moles of another element in that compound. So let's entertain the first use of our mole ratio. Let's entertain the first way of looking at our mole ratio, which is a way of converting from molecules to atoms. So looking at N2O5, let's draw just a picture of N2O5. Just in terms of drawing out each of my element symbols. So my first question to all of you is, how many moles of nitrogen do we have per mole of N2O5? So in one molecule of N2O5, how many nitrogens do we see? How many nitrogens do we have? We have 2, yeah. So we have 2 moles of nitrogen per 1 mole of N2O5. Now let's look at another ratio. How many moles of oxygen do we have per mole of N2O5? What is our mole to mole ratio? How many moles of oxygen do we see? How many oxygens do we see? 5. Yep, so we have 5 moles of oxygen per 1 mole of N2O5. Now let's get a little bit fancy, and I'd like you to tell me, how many moles of nitrogen do we have per mole of oxygen? How many moles of nitrogen do we have per mole of oxygen? So first, how many nitrogens do we see? So first, how many nitrogens did we see? 2. And how many oxygens did we see in the same compound? 5, yep. So we have 2 moles of nitrogen per 5 moles of oxygen. Okay. So now, with this idea in mind, let's answer the question, how many moles of nitrogen are in 13.5 moles of N2O5? Well, first and foremost, we're going from moles of N2O5 to moles of nitrogen. Okay. So then, starting off with 13.5 moles of N2O5, if we're going from moles of N2O5 to moles of nitrogen, what units do we want on top? What units do we need on top of our denominator? Sorry, yes, what units do we need on top? If we're going...
Nitrogen.
Yep, exactly. So we need moles of nitrogen on top. And if we're going from the moles of N2O5, what units do we need on the bottom? What units do we need on the bottom?
N2O5.
Yep, exactly right. And we know this ratio already. We figured it out up here. There are 2 moles of nitrogen for every 1 mole of N2O5. So if we punch this into our calculator, we get 27.0 moles of nitrogen. Does this make sense to everyone so far? How we're able to use the formula to calculate the moles of an element from the moles of a compound. Let's do another example. We're asked how many moles of nitrogen are in a sample of N2O5 containing 4 moles of oxygen. So we're going from moles of oxygen to moles of nitrogen. And from here, we use our formula. So in this case, our formula is N2O5. So let's write out our initial units. We have 4.0 moles of oxygen. If we're going from moles of oxygen to moles of nitrogen, what units go on top? What units go on top? Don't worry, it's not a trick question. What units are going to go on top if we go from moles of oxygen to moles of nitrogen? If we're going to moles of nitrogen, what units will be on top? Nitrogen, exactly. And what units will be on the bottom this time? What units will be on the bottom? If we're going from the moles of oxygen will be on the bottom. And we already have that ratio. We know that there are 2 moles of nitrogen for every 5 moles of oxygen. Moles of oxygen cancel. And let's just quickly punch that into our calculator. And that in turn gives us 1.6 moles of nitrogen. Do these examples make sense so far? Is everyone comfortable using the formula for unit conversions? Any questions so far? If not, let's continue on with the next set. In this case, you can submit your responses in the chat or via Canvas quiz 4.4. And I'd like you to, looking at the following formula, tell me how many moles of carbon are in 5.5 moles of C2H4. And then I'd like you to tell me how many moles of hydrogen are in a sample of C2H4 containing 3 moles of carbon. And I would recommend in this space above trying to write out a few of the relevant formula ratios. So we'll take about 4 to 5 minutes to work through this example, and then we'll come together to discuss, and I'll be checking to see how the class is responding via Canvas and in the chat, just to get a sense of what focused feedback I can provide. And if you would like me to provide feedback on your answer in more detail, don't be shy to message me with your proposed response. We're already seeing some the reason for that is because in the note set, the numbering I was trying to respect the numbering in the note set as closely as possible, just so that way I didn't want to renumber it and have the quizzes get shuffled. And the intent was that those quizzes would be bundled together, but I split them into pieces just to make it a little bit easier to navigate. Let's try to get a few more responses via Canvas and in the chat, and we'll discuss in about another 3 minutes. Let's try to get a few more responses in the chat or via Canvas. And if you're unsure, don't be shy to ask questions via the chat. So the responses in the chat I'm receiving so far are looking good. Just remember that you're multiplying by the subscript if you're going from molecules to the moles of an element. So if you're going from moles of a molecule to moles of an element, you're going to want to multiply by the subscript rather than divide. And since we're already in moles, we don't have to worry about the molar mass or anything like that. We're just using the formula right now to generate our conversion factors. And we'll discuss in about another minute. I'm already seeing a range of reasonable responses via the Canvas responses, and we'll discuss momentarily. Okay, so let's discuss this example now. So in C2H4, just to draw a crude picture just to help us count atoms, we have the following relationships. We know we have 2 moles of carbon per 1 mole of C2H4. We have 4 moles of hydrogen per 1 mole of C2H4. And we have 2 moles of carbon per 4 moles of hydrogen in this compound. Okay, so in the first question we're prompted, how many moles of carbon are in 5.5 moles of C2H4? So we're going from moles of C2H4 to moles of carbon. Wonderful. So we have 5.5 moles of C2H4. Okay, and now if we're going to, sorry about that, there was a small graphical error in OneNote. So now if we're going from moles of C2H4 to moles of carbon, what units need to be on top? If we're going to moles of carbon, what units are we going to have on top?
2 moles carbon.
Yep, exactly right. So we're looking at moles of carbon per mole of C2H4. And looking at our formula, we see that we have 2 moles of carbon per 1 mole of C2H4. The moles of C2H4 cancel, and we're left with 11 moles of carbon. Does this make sense to everyone so far? So we're just doing a conversion from the moles of molecules to the moles of the atoms in that molecule. Let's try another, continue on and let's discuss the next part of this example. So we're asked to figure out the moles of hydrogen in a sample containing 3 moles of carbon. So we're trying to go from moles of carbon to moles of hydrogen. Okay. We have 3.0 moles of carbon. And now if in order to complete our unit conversion, if we're going from moles of carbon to moles of hydrogen, what units do we need on top? What units do we need on top? Moles of hydrogen, exactly right. And what units do we need on the bottom? What units are we going from? What units are we trying to cancel? What units are we trying to get rid of? What units are we going from? Carbon, exactly right. So we're trying to cancel the moles of carbon. So looking at our formula, we see that we have 4 moles of hydrogen per every 2 moles of carbon. Moles of carbon cancels, and that gives us 6.0 moles of hydrogen. Any questions on these examples? Any questions on these examples? If not, let's continue on. And let's talk about the next way we can use the chemical formula. The chemical formula also provides a relationship between the raw number of molecules and the number of atoms of an element. So now we're looking at the total number of atoms and molecules. So the chemical formula also provides a relationship between the atoms of one element and the atoms of another element. So for example, in B2H6, and now pay attention to these units now. How many atoms of boron do we have per molecule of B2H6? So if this entire collection of atoms is one molecule, how many atoms of boron do we have per molecule? How many atoms of boron do we have per molecule? How many boron symbols do you see? 2. So we have 2 atoms of boron per 1 molecule of B2H6. Now, we've essentially gone from a mole ratio to an atom and molecule ratio. So this is useful for particle to particle conversions. Likewise, if we look at the atoms of hydrogen per molecule of B2H6, we can clearly see that we have 6 atoms of hydrogen per 1 molecule of B2H6. Finally, if we want to do an atom-to-atom relationship, how many atoms of boron do we have per atom of hydrogen, or per atoms of hydrogen? What is our atom-to-atom ratio? Yep, exactly right. So we have 2 atoms of boron per 6 atoms of hydrogen. Perfect. So we're used to looking at our chemical formula and generating these formula ratios. Wonderful. So let's apply this. So we're asked how many atoms of boron are in a sample that contains 1.5 times 10 to the 20th molecules of B2H6. So we're going from molecules of B2H6 to atoms of boron. So if we have 1.5 times 10 to the 20th molecules of B2H6, looking at our final units. So looking at our final units, what units do we need on top? What units do we need on top? If we're going from molecules to atoms, what units do we need on top?
2 atoms of boron.
Yep, exactly right. And we already established there are 2 atoms of boron in 1 molecule of B2H6. And that in turn gives us, after punching it into our calculator, 3.0 times 10 to the 20th boron atoms. So the logic is exactly identical. The logic is exactly identical to how we handled the mole to mole conversions. The only difference now is that we're using units of atoms and molecules in our formula ratio. Let's do another example to drive home this point. We're asked how many atoms of hydrogen are in a sample that contains 3.0 times 10 to the 19th atoms of boron. So we're going from atoms of boron to atoms of hydrogen. So then entering our starting units, we have 3.0 times 10 to the 19th atoms of boron. Okay. And now if we're going to atoms of hydrogen, what units need to be on top? If we're going to atoms of hydrogen, what units need to be on top?
6.
Yep. So we'd have atoms of hydrogen per atoms of boron. And in the formula B2H6, how many atoms of hydrogen do we have per atom of boron? What is our ratio? What is our ratio in this case?
62.
Yep, exactly. We have 6 atoms of hydrogen per 2 atoms of boron. And that in turn gives us 9.0 times 10 to the 19th atoms of hydrogen. Okay. Any questions on these examples? Any questions on these examples? If not, let's work on a problem solving set. This is found in Canvas Quiz 4.4. Given the following formula, I'd like you to answer the following 2 questions. How many atoms of sulfur are in a sample that contains 2.2 times 10 to the 18th molecules of S3Cl5? And then in the second part, I'd like you to tell me how many atoms of chlorine are in a sample of S3Cl5 that contains 7.3 times 10 to the 12th atoms of sulfur. So let's spend about 4 minutes working through this problem, and then we'll come together as a group to discuss. Don't be shy to submit your responses via Canvas, via private message in the Zoom chat, or by typing your proposed response directly in the public Zoom chat. And just to make it easier, so that way the Canvas quizzes are distinguishable, I labeled this Canvas exercise as 4.4.1. And we'll discuss in about 4 minutes. And checking to see, we already have some reasonable responses so far via Canvas. Let's try to get a few more responses, both via Canvas or in the chat. And then we'll discuss this problem in about another 2 to 3 minutes. Ah. Are you checking the quiz 4.4.1? That should fix the issue of the quiz questions looking different. Yeah, I had to tune the numbers a little bit in order to make them easily entered into Canvas. Since Canvas doesn't handle large numbers particularly well, so I had to change the numbers a little bit in Canvas. So let's spend about another minute on this problem. We have a reasonable number of responses and the responses look perfect. So let's try to get a few more responses and then we'll discuss. So let's talk through this problem. So we're asked how many atoms of sulfur on our sample that contains 2.2 times 10 to the 18th molecules of trisulfur pentachloride. Okay, so starting off, we're trying to go from molecules of S3Cl5 to atoms of sulfur. Okay, so starting off, when we write our initial units of 2.2 times 10 to the 18th molecules of S3Cl5, if we're going from molecules to atoms, what units do we need to have on top? What units do we need to have on top? If we're going from molecules of S3Cl5 to atoms of sulfur, what units do I need to have on top?
Atoms of sulfur.
Yep, exactly right. And how many atoms of sulfur do we see in our formula? How many atoms of sulfur do we see?
3.
3, yep. So we have 3 atoms of sulfur per 1 molecule of S3Cl5. And if we punch that into the calculator, that gives us 6.6 times 10 to the 18th atoms of sulfur. Wonderful. So let's do another example. We're asked how many atoms of chlorine are in a sample that contains 7.3 times 10 to the 12th atoms of sulfur. Of course, noting this is a sample of S3Cl5, as these two problems are bundled together in a way. So we're trying to go from atoms of sulfur to atoms of chlorine using our formula ratio. So starting off, we have 7.3 times 10 to the 12th atoms of sulfur. And if we're going to atoms of chlorine will be on top. And atoms of sulfur will be on the bottom. So my question to all of you is, how many atoms of chlorine do we have? How many atoms of chlorine do we have?
5.
Yep. And how many atoms of sulfur do we have?
3.
Perfect. So now let's punch that into our calculator. So we have 7.3 times 10 to the 12th times 5 over 3. And that in turn gives us 1.2 times 10 to the 13th chlorine atoms. Perfect. Any question on these examples? Any questions on these examples? If not, let's continue on with the next set of examples. This time, we're looking at multi-step mass to mole conversions. And I made this little chart just to help everyone develop a general scheme for solving these problems, though I highly recommend just focusing on the unit analysis. So to go from grams to moles, we're going to divide by the molar mass. To go from moles to atoms, we're going to use our formula ratio. And if we want to go from moles to grams, we multiply by our molar mass. Okay, so let's apply this. Things are best learned via application. So we're asked to calculate the moles of chlorine and 16.0 grams of carbon tetrachloride. So we're trying to go from grams of carbon tetrachloride to something to moles of chlorine. Now, what is our intermediate unit? What is our stepping stone unit? What units are going to go in the middle here? If you're setting this problem up on an exam, for example, what units will you go through here? I'm given the mass of carbon tetrachloride. I want to get the moles of chlorine. What units go in the middle here? What units do I need to go through to complete this conversion? Atoms would be tricky since we are starting with the mass of a molecular species. What other units could we go through? If we want to go and figure out the moles of chlorine, where can we get the moles of chlorine if we know the mass of carbon tetrachloride? What units are we going to go through here? And if you need a hint, just try to look up here at this problem solving scheme. Yes, we can get the moles of chlorine from the mass. Sure. That is a possibility, but we don't have the mass of chlorine given, so that's a little tricky. If we have the grams of carbon tetrachloride, what can we calculate almost immediately? What can we calculate if we know the grams of carbon tetrachloride? We can use the molar mass and we can calculate the moles of carbon tetrachloride. Now, I'd say probably the best way to get really fast at solving these problems is to just focus on figuring out how to write these unit schemes. What do I have? What am I trying to get to? What units am I going through? Now, the reason why we're going to moles of carbon tetrachloride, we can easily calculate it from the mass. And once we have the moles of carbon tetrachloride, we have the formula and we can use it to get the moles of chlorine. So then let's apply what we know. So we have 16.0 grams of carbon tetrachloride. And we're going to need to do a sidebar calculation for the molar mass. So we have 12 plus 35.5 times 4. Let's do that really quickly. And that in turn gives us a molar mass of 154 gram per mole. So for our 16 grams of carbon tetrachloride, if we're going from grams to moles of carbon tetrachloride, I'd need moles of carbon tetrachloride on top, and I'd put grams of carbon tetrachloride on the bottom. So in 1 mole of carbon tetrachloride, I have 154 grams. Now, if we're going from moles of carbon tetrachloride to moles of chlorine, my question to you is, how many moles of chlorine do we have per mole of carbon tetrachloride? How many chlorines do we see in the formula CCl4? How many moles of chlorine do we have? 4. So we have 4 moles of chlorine per 1 mole of carbon tetrachloride. Okay, now, if you look at the units, you see grams cancel and moles cancel. And if we punch this into our calculator, we get 16 over 154 times 4. That in turn gives us 0.416 moles of chlorine. Okay, let's do another example. In this case, we're asked what mass of C2H2 contains 4 moles of carbon. So we're trying to go from moles of carbon to moles of acetylene, which is C2H2. To grams of acetylene, not quite moles. So we want the mass, which is the grams of acetylene, and we're given the moles of carbon. So what is our stepping stone? What is our intermediate unit? What units are we going through to convert between moles of carbon to grams of acetylene? What is our intermediate unit?
Moles of C2H2.
Yep, exactly right. So now that we have that scheme worked out, just as a sidebar, we're going to calculate the molar mass of C2H2. So we have 12 times 2 plus 1 times 2. That gives us 26 gram per mole. So plugging in our moles of carbon is 4.0 moles of carbon. Now, looking at this expression, how many moles of C2H2 do we have per every mole of carbon in our sample? So what's our mole to mole ratio? How many moles of carbon do we see? How many moles of carbon do we see based on our formula ratio? What's our moles of carbon per mole of C2H2? How many carbons do we have?
2 to 1.
Yep, exactly. We have 2 moles of carbon per 1 mole of C2H2. Okay. Then if we're going from moles of C2H2 to grams of C2H2, otherwise known as acetylene, we know that we have 26 grams per 1 mole of C2H2. Moles cancel, moles of acetylene cancels, moles of carbon cancels, and we're left with 52 grams of acetylene. Do these examples make sense to everyone so far? Any questions so far on these examples? If not, let's try to apply our knowledge to a few examples. So this is found, and you can submit your responses via the chat or Canvas quiz 4.4.2. And let's try to answer the following 2 questions. What mass of nitrogen triiodide contains 5 grams of iodine? and how many moles of sulfur are in 32 grams of hydrogen sulfide. So let's spend a few minutes working through these problems, and then we'll come together as a group to discuss momentarily. And don't be shy to submit your responses via Canvas or via the chat feature. And we'll discuss in about 4 minutes. And I'm already seeing some reasonable responses in the chat or via Canvas. Let's try to get a few more responses and we'll discuss in about 3 minutes. Let's try to get a few more responses, and if there are any questions when working through these two problems, don't be shy to message me via the chat or unmute and ask your questions verbally. These are the bread and butter questions that you'll likely see on exams, as they're wonderful at testing if you understand how to use each of the conversion factors we've covered so far in this chapter. Let's try to get a few more responses and we'll discuss in about 2 minutes, but if everyone needs a little more time before they can formulate and double check their responses, well, I want to give everyone enough time where they can propose a reasonable solution and then revise or make notes once they see the instructor solution. So we're getting a few more responses via Canvas. Let's spend about another minute to a minute and a half on this problem. And if there are any questions when working through these examples, please don't be shy to ask. Okay, so let's discuss this example. So we're asked to figure out what mass of nitrogen triiodide contains 5 grams of iodine. Okay, so first we need to figure out the formula. So for nitrogen triiodide, the formula is 1 nitrogen with 3 iodines. Now that we have the formula, we can calculate the molar mass, which is the mass of nitrogen, which is 14 gram per mole, plus the mass of iodine, which is 126.9 gram per mole, times 3 for our 3 iodine atoms. So punching that into our calculator, that in turn gives us a molar mass of 394.7 gram per mole. So now looking at what we have to do in terms of a problem solving scheme, we have 5 grams of iodine. And when we see the name of an element in these sort of composition problems, it's referring to the mass of that element in its atomic form. More on that later. So we have 5 grams of iodine, and we are trying to calculate the grams of nitrogen triiodide. Okay. So then, from this information, if we know the mass of iodine, how can we relate the mass of iodine to the mass of nitrogen triiodide? What intermediate units are we going to use? What intermediate units are we going to use?
You go from moles of iodine on top,
Yep.
and then on the bottom is grams of iodine for the first
Yep.
one.
Okay, perfect. And now to go from moles of iodine to grams of nitrogen triiodide, what intermediate units are we going to go through? Just the intermediate unit for now.
Oh, moles of nitrogen triiodide.
Yep, exactly right. Okay, perfect. So now that we have our scheme, exactly as mentioned, we're going to execute on that scheme. So for 5 grams of iodine, to go from grams of iodine to moles of iodine, we know that in 1 mole of iodine, we have 126.9 grams. Now, to go from moles of iodine to moles of nitrogen triiodide, my question to everyone is how many, in 1 mole of nitrogen triiodide, how many moles of iodine do we have? So in 1 mole of nitrogen triiodide, how many iodine atoms do we have? How many moles of iodine do we have?
3.
3, exactly right. And then finally, to go from moles of nitrogen triiodide to grams, we know we have 394.7 grams per 1 mole of nitrogen triiodide. Now let's punch this into our calculator. We have 5 over 126.9 times 1/3 times 394.7, and that in turn gives us 5.2 grams of nitrogen triiodide. So as I didn't see a ton of responses for this Canvas quiz, I'd like everyone to take about another 2 minutes, and considering what we've covered for this first example, I'd like you to reattempt this second problem. Maybe revise your solution, look over your solution, and then let's try to get a few more responses in the chat or via Canvas for the second part of this Canvas quiz and the second part of this problem solving session. And don't be shy to message me with your questions, or proposed responses? And we'll discuss in about another 1.5 to 2 minutes. And we'll discuss in about another minute. So checking Canvas, let's try to see. We're getting a few more responses, and the responses look quite good. So it's encouraging so far. I always want to give students the opportunity, after seeing a proposed solution to a problem, the opportunity to revise their problem solving. So we'll discuss in about another 30 seconds to a minute. Okay, so let's discuss this next example. We're asked to figure out the moles of sulfur and 32 grams of hydrogen sulfide. So hydrogen sulfide, this is naming conventions associated with a binary acid in the gas phase. So hydrogen, H plus, sulfide, S2 minus. We cross our charges and we get H2S. The molar mass of hydrogen sulfide is 32 gram per mole plus 1 gram per mole times 2, which gives us 34 gram per mole. Wonderful. So starting off, we're given the grams of hydrogen sulfide, and we want to calculate the moles of sulfur. So what is our intermediate unit? What unit are we going through in this example? What is our intermediate stepping stone? What's our intermediate unit?
Moles of hydrogen sulfide.
Yep, exactly right. So then, starting off, if we have 32.0 grams of hydrogen sulfide, in 1 mole of hydrogen sulfide, we know we have 34 grams. And now to finish off this problem, how many moles of sulfur do we have per mole of hydrogen sulfide? What is our mole to mole ratio in this case? How many moles of sulfur do we see?
1-to-1.
Yep, exactly right. So if we punch this into our calculator, we get 0.941 moles of sulfur. Any questions on these examples? If not, let's continue on and let's do another guided example. This time we're really chaining together all of the conversion factors that we've learned to go from grams to moles of molecules to moles of atoms to just atoms. And remember, to go from moles to atoms, we use Avogadro's number. So in this case, we're asked how many potassium ions are in 3 grams of potassium phosphide. Okay. So just as a starting precaution, let's calculate the molar mass, which is 39. Let's see, for potassium, let me look up in our periodic table the molar mass of potassium. Potassium is 39 gram per mole times 3 potassium atoms plus phosphorus, which is 30.9 gram per mole times 1 phosphorus atom. And that in turn gives us a molar mass of 147.9 gram per mole. Okay, now we're ready to make a problem-solving scheme. So we're asked to go from the grams of potassium phosphide, and in the end, we want to calculate the number of potassium ions. Think of the word potassium ions like potassium atoms. Now, where do we get atoms from? So where am I going to get the atoms of potassium from? What unit am I going to go through right before? What units do I need to calculate potassium ions? So if we want to calculate atoms, we need what? If we're trying to calculate atoms, we'd need what?
Moles?
Yep. And moles of what in this case? Moles of. So if we're calculating potassium ions, we need the moles of what was that?
Moles of potassium?
Yep, exactly right. Okay. Now where are we going to get the moles of potassium from if we have the mass of potassium phosphide? Where are we going to get the moles of potassium from?
The molar mass?
Yes, but we don't have the mass of potassium directly. So how do we calculate the mass of an atom in a how do we calculate the moles of an atom in a compound? So to go calculate the moles of atoms, we need the moles of our molecule, which would be the moles of potassium phosphide. So you get the moles of the atom from the moles of your molecule. So now that we have our problem-solving scheme created, and this is what I would practice if you're developing and you want to develop the skills associated with problem solving, because if you can set up the unit scheme, lining up the conversion factors is very straightforward. So if we have 3.0 grams of potassium phosphide, so first and foremost, in 1 mole of potassium phosphide, how many grams do we have? We know that. We calculate it to be 147.9 grams. Now, to go from moles of potassium phosphide to moles of potassium, let's now answer the question, how many moles of potassium do we have per mole of potassium phosphide? What is our mole to mole ratio? How many potassium ions do we see? How many potassium ions do we see?
3.
3, yep. So we have 3 moles of potassium per 1 mole of potassium phosphide. So our grams cancel, our moles potassium phosphide cancels. And now if we want to go from moles to atoms, so how many potassium plus atoms are present in 1 mole of potassium plus? What number do we use to count atoms per mole? What do we call that number? For
Avogadro's number.
Yep, exactly right. So let's plug that in. So we have 6.02 times 10 to the 23rd potassium ions per mole of potassium. So let's now punch this into our calculator. We have 3 over 147.9 times 3 times 6.02 times 10 to the 23rd. And that in turn gives us 3.7 times 10 to the 22nd potassium ions. Any questions on this example? So, if there aren't any questions, let's now try to apply what we've learned to the following example. So this can be answered in the chat, or you can submit your responses via Canvas quiz 4.3.3. And I'd like you to calculate how many atoms of oxygen are in 32 grams of phosphoric acid. And we'll discuss this example in about 4 minutes. And I'll be checking Canvas and responses in the chat just to see how everyone in the chat is doing and if there are any questions or common errors that I can address. And we'll discuss in about 3 to 4 minutes. So looking at the Canvas quiz, we already have a few reasonable responses so far. Let's try to get a few more responses via Canvas and chat. And if there are any questions at all, really don't hesitate to ask. If not, we'll discuss in about 1.5 to 2 minutes. Yeah. So in Canvas, I changed the number just so that way it works so that way it allows you to enter the number more easily in Canvas. I just changed the magnitude. and we'll discuss in approximately a minute to a minute and a half. Okay, so let's discuss this next example. So we're asked to figure out the atoms of oxygen in 32 grams of phosphoric acid. So first things first, let's calculate the molar mass of phosphoric acid. So we have 1 gram per mole for hydrogen, and we have 3 hydrogen atoms. We have 30.9 gram per mole for phosphorus, and we have 1 phosphorus atom. And we have 16.0 gram per mole for oxygen, and we have 4 oxygen atoms. So punching that into our calculator, we have 16 times 4 plus 30.9 plus 3. And that in turn gives us a molar mass of 97.9 gram per mole. Okay. Now from here, we're starting off with the grams of phosphoric acid, and we are trying to calculate the atoms of oxygen. So where are we going to get the atoms of oxygen? Where are we going to get the atoms of oxygen from in this case? How do we calculate the atoms of oxygen?
From moles of oxygen.
Yep, exactly right. So from the atoms of oxygen, we can in turn calculate the atoms of oxygen from the moles of oxygen. Now, where are we going to get the moles of oxygen from in this case? Where are we going to get the moles of oxygen from in this case? How do we calculate the moles of oxygen if we're given the mass of phosphoric acid? What unit?
Moles of phosphoric acid.
Yep, exactly right. So we're going to calculate the moles of oxygen from the moles of phosphoric acid, which we can get from the grams of phosphoric acid. So now that we have this problem laid out for us, let's execute. So if we have 32 grams of phosphoric acid, let me just fix the 3. There we go. We know first and foremost from our molar mass that in 1 mole of phosphoric acid, we have 97.9 grams. Additionally, we know for looking at our formula, let's try to answer the question, how many moles of oxygen do we have per mole of phosphoric acid? How many moles of oxygen do we have in the formula? And don't be shy to respond in the chat or verbally. So I see in the chat we have 4 moles of oxygen per mole of phosphoric acid. That's exactly right. Finally, if we're going from moles to atoms, we use Avogadro's number, which means we have 6.02 times 10 to the 23rd atoms per 1 mole of oxygen. The moles of oxygen cancel. Let me fill this in. The moles of phosphoric acid cancel, and the grams of phosphoric acid cancels. Now let's punch this into our calculator. We get 32 over 97.9 times 4 times 6.02 times 10 to the 23rd. And that in turn gives us 7.9 times 10 to the 23rd atoms of oxygen. Do these examples make sense so far? Any questions so far? Overall, looking at the Canvas quiz responses, the class is doing quite well. And if you want to reattempt any of these examples, they are all found on Canvas. And I really encourage you to use them as a study tool. Avogadro's number has units of atoms per mole. So anytime we're going from moles of an element, so moles of an element, to atoms, or if we're going from moles of a compound to molecules, you will use Avogadro's number. Avogadro's number relates moles of particles to the total number of that particle. Did that answer your question? So Avogadro's number allows you to convert between atoms and moles. Perfect. So let's do a few more examples. So this time, this is known as an equivalency problem. In this case, we're relating the grams of one element to the grams of another element. So to do this, we're going to need to figure out a relationship between the moles of each of our elements using our formula ratio. So let's show how this would work in practice. So it's asking how many grams of nitrogen are there in a sample of ammonium nitrate with 4 grams of hydrogen. So when Canvas has a slightly different number, you'd solve the problem in our note set, and then all you do is you change the number that you start inputting into your calculator to the number in Canvas. I just had to change the magnitude of the numbers so that way you can enter it in Canvas, because Canvas doesn't like very large or very small numbers. So in this example, we're trying to figure out how many grams of nitrogen are there in a sample of ammonium nitrate with 4 grams of hydrogen. So for ammonium nitrate, we have a name. We're going to need to figure out a formula for that name. So would someone like to volunteer and tell me what is the formula of ammonium nitrate? Don't be shy to type it in the chat or unmute and provide me the formula, or you can provide the formula of one of the ions in ammonium nitrate. But what, yep.
I think the formula is NH4
Yep.
NO3.
Yep, exactly right. So to
Okay.
show the logic, we have ammonium, which is NH4 plus, nitrate, which is NO3 minus. We cross our charges and we get NH4 NO3. Okay, now we don't have to get carried away and calculate the molar mass just yet. Let's make our problem solving scheme and see what data we actually need. So we're given the grams of hydrogen and we're asked to calculate the grams of nitrogen. Okay, now working backwards, I like to think about things retrosynthetically. So if you have your grams of nitrogen, where are we going to get the grams of nitrogen from? How do we calculate mass typically? We calculate mass from what unit?
Moles of nitrogen.
Moles. Yep. Okay. And where are we going to get the moles of nitrogen from if we have our formula right there? And we have the grams of hydrogen. Where are we going to calculate the moles of nitrogen from? If we're given the grams of hydrogen.
Would it be moles of ammonium nitrate?
You can do it that way, but there's actually a faster route. If we're given the grams of hydrogen and our formula can relate hydrogen and nitrogen, can we get the moles of nitrogen from something else?
Just moles of hydrogen.
Yep, exactly right. Perfect. So now we have our problem-solving scheme established. So starting off, let's write our units. So we have 4 grams of hydrogen. We know in 1 mole of hydrogen, remember the unit that we're converting to goes on top. In 1 mole of hydrogen, we have 1 gram. And now, looking at this formula for ammonium nitrate, I'm just going to draw a little picture just to help everyone see what's going on. I always like to draw pictures. You may say, oh, the pictures are a little silly. Doesn't matter. They help you reach a solution efficiently, so it doesn't matter how silly it looks. So my question to all of you is, how many moles of nitrogen do we see per mole of hydrogen? What's our ratio of nitrogen to hydrogen looking at this picture of our formula?
2 to 4.
Yep, so we have 2 moles of nitrogen, 1, 2, per every 4 moles of hydrogen. Wonderful. Now let's continue on. We're going from moles of nitrogen to grams of nitrogen. And we know from our atomic mass, we have 14 grams of nitrogen per 1 mole of nitrogen. Let's now plug this into our calculator. We have 4 over 1 times 2 over 4 times 14. And that in turn gives us 28 grams of nitrogen. Does this example make sense to everyone so far? So to apply what we've learned, let's work on our final example for today, which is Canvas Quiz 4.3.4. And let's try to solve the following problem together, and we'll spend about 4 minutes on it. Let's try to figure out how many grams of chlorine are in a sample of chlorous acid that has 16 grams of oxygen. So you're going to need to get the formula all set for this compound. And I'll be checking Canvas and the chat to see how everyone's doing, working through. Let's try to get a few more responses in the chat and Canvas. I already see 2 reasonable responses via Canvas. Let's try to get a few more, just so that way at least we have reasonable progress before we discuss our solution. So that way you can check your solution and revise any potential discrepancies. And we'll discuss in about another 1.5 to 2 minutes. And if there are any questions, don't be shy to ask them in the chat or verbally. And we'll discuss in about another 30 seconds to a minute. It's encouraging. We have a fair portion of submitted responses for this problem solving session, and they're all quite good. So let's discuss this last example. So first and foremost, chlorous acid. Would someone like to volunteer and provide us the formula for chlorous acid? Chlorous acid. HClO2, exactly right. This is derived from the name chlorite, which is ClO2 minus. We cross it with H plus, and that gets us chlorous acid. Wonderful. So we're given the grams of oxygen, and we need to figure out the grams of chlorine as our intermediate units. We're going to get the grams of chlorine from the moles of chlorine, and from the moles of chlorine. If we have the formula, we can figure out the moles of chlorine from the moles of oxygen. So now that we have the following scheme prepared, in our next step, what we're going to do is we're going to start off with our number, which is 16 grams of oxygen. We can get the moles of oxygen using our atomic mass. In 1 mole of oxygen, we have 16 grams of oxygen. Okay, now looking at our formula, how many moles of chlorine do we have per how many moles of oxygen? What is our mole to mole ratio? How many moles of chlorine do we have, and how many moles of oxygen do we have? Is it a 1-to-1, a 2-to-1? What's our ratio? One to 2. We have 1 mole of chlorine for 2 moles of oxygen. Next, we're going to go from moles of chlorine to grams of chlorine, given that we have 35.5 grams of chlorine in 1 mole of chlorine. So moles of oxygen cancels, moles of chlorine cancels. And if we enter this into our calculator, we have 1 over 2 times 35.5. And that in turn gives us 17.7 grams that we in turn round to 18 grams of chlorine. Any questions on this example? Any questions on this example? Is everyone feeling a little more comfortable with using all of these conversion factors, all of these tools that we've developed to solve chemical problems? Okay, so as we are at the end of our scheduled session, we'll resume in 40 minutes for laboratory.